Well, so there will be some techniques to start with. So the first, we can tolerate. So this is a randomized technique we assign. So we usually then put as a graph, we assign random colors in some way, and we do something. So we have to do exercises, then dynamic programming. And I think that will be an easy topic for you because nothing new. And then what you already know, the direction technique. So now I will speak about feedback vertex. So the problem here will be set cover. Then the famous problem of feedback. Okay, you don't know it, so I need to write it. Then last time I promised a kernel for vertex cover problem of linear size. So kernels is another technique of size grouping. And then there's tree decomposition. Maybe we will not finish everything, but then you just continue next week. And the topic for next week, it will be the last, it will be to prove that there is no FPT algorithm. So there exists some theory. Like if you want to exclude the possibility of that the problem is not in P, you can prove it's NP hard or NP complete. And so we can, we have another class, it's called W1, and sometimes you need W2. And you can prove that the problem is the W1 complete, and then you understand there is no FPT algorithm. And so the conjecture here, so for normal computational complexity, you assume P different from NP. Now we will assume FPT different from W1. But it's all the same idea. So, but we need to define this for next week. So don't worry if you don't understand anything. But so we will define what is this class W1. It's a bit complicated. And then, yeah, we will, but we will, it's easier to do it directly from exponential time hypothesis. I mentioned it last week. Okay, but this is all for next week. So now we just prove some fun algorithms. We present some fun algorithms because usually software engineering, it's important to know the techniques so that when there is a paper and your boss wants to implement it, you already seen it before and it's less scary. Okay, so we will start with coloring. Also, I barely prepared the lecture, so it will be I'm curious, and now I didn't sleep much, so I hope I will teach a bit slower and might need some help to remember everything. Okay, yeah, that's good. Yeah, we all have the problem.
For the sake of synchronizing the tempo.
Yeah. Okay. So let's start with the coloring technique. So the problem is a K-pot problem. So you get a graph and a number K. Can you find a simple path of node K? It means no repeated nodes, simple path. I mean, path is by default simple, but of course, if you can repeat nodes, it's a very easy problem. Okay, let me write it. And this problem, it's easy to understand, it's NP-complete. So why? It's one of the most famous NP-complete problems.
Because it reduces to something like this.
Hamiltonian path problem. Yeah. So if K
It's exactly this.
yeah, if K equals the number of nodes, then yeah. So and graph. Okay. Question. This is simple. And so the algorithm. So we want to give now we're speaking about a randomized variant of FPT. But it's clear what it means. Okay, let us recall what is FPT. So a parameterized problem. Now, so there are two inputs, the parameters and then the language. Was that this and that means there's a constant C function, the computable function. Just what we set last and just repeating. And an algorithm that solves a problem in time. So you remember, so sorry, that an algorithm that decides the x in L in time times length of x. And so, and there was sloppy, I said to the power c, but the correct definition is length of x plus k to the power c. So I didn't write the plus p here, but for today it doesn't matter. Why is it different? I was lazy last time. I want to make things simple to prove the theorem. But I got it doesn't matter for our discussion.
I mean, why is it different? If we can just link the part to the end, so we can.
Oh, so yeah, good question. So if x is equal to 1, well, the thing is that yeah, it's yeah, it's probably the same. Yeah, you're right. It's the same. Sorry. Okay.
Could you please explain what is FPT in more intuitive way?
Okay. So if the parameter is small, then the runtime is reasonable.
Okay.
That's the intuition. But the exponent does not depend on the parameter. So it needs to be very reasonable. Like we discussed about the clique problem, we can solve it in time. So for a graph with n nodes in time n to the power k, that's basically n to the power k. And so brute force algorithm is not an FPT algorithm. And the next lesson we will see for clique, we cannot hope for better. I mean, it's very unlikely. You can do you can get rid of the power, the k and the exponent. So this will be unlikely. But for all these, today we will see many problems so we can get to it.
Well, the function can depend on the length of the input and the parameter, right?
So the functional
Function can depend on the length of, then we cannot just erase plus key because it's like how do we do it? It's a Newton below.
No, as soon as the length of x is 1, then the plus k can become a factor k. It is anyway bigger, so that's why you're right. It's the same.
As soon as length of x is
Yeah. So, but we cannot have a length of x to the power k is not allowed in our theory.
Yes. But
But we can have
K-
k in the
K-
linear
K-
constant.
k
the
times
front.
like k times the length of x.
Yeah.
Is it allowed?
So, but this is allowed for us. To the power 100. It is
yeah.
okay.
You can't
No,
just
no, I mean,
erase k.
no, I mean,
No, but I think you're right
Because
because
it will be x times something k. Something x times something k.
can we multiply?
yeah, but you can always put a k to the in the front. A k to the power c that you can always put in the front.
Yeah, but all the other k.
Like we have k to the power c minus 1 times x.
So if the length of x is big, and then we add k, then the length of x can at most double. So we have this to the c, but this is so if length of x is bigger than k, then this is bounded by 2 to the power c, length of x to the power c, right? If we believe this. So in this case, the dropping k doesn't harm. And in the other case, if x is smaller than k, then we're also good. Because we can put the factor 2k to the power c, we can absorb in the f of k. So your comment that I don't need to write k here, it doesn't matter. It was very clever of you.
Now it's actually
Yeah.
yes.
I didn't understand any of that. Not any of that. I didn't understand before.
Now we see.
But
Yeah, you're very nice.
Do we take small or big O of this expressions? I don't know. Big O of f of k times x to the power c, or do we take
It doesn't matter also because you can always hard code a finite number of inputs in your algorithm, so it answers very quickly. Okay, maybe for x length of x equal 1 and 0. So, but people usually write it like this, but you can take big O, and then unless you're very pedantic on inputs of length 0 and 1, it doesn't change anything. Because just if you have any computable function that's so much power. Yeah. Actually, mathematically, I should do with this. This case is just 0 and 1 input.
We can trust you when they don't matter.
Yeah, it's in the RAM model, you can just in one step check whether the input x is short and give the answer. And so then the runtime is just 1, and then it's fine. And then for the other cases, so usually no Turing machines are used. But we will use circuits in the next lecture as model. So yeah. They're clever guys who don't bother. Yeah, they're so used to knowing all this theory that they don't bother. Okay, but now it's time. So yeah, but actually a very good point. So there is easy algorithm. We try all k element subsets and check whether they form a path. So but then we don't have FPT algorithm because that's just time again. And to the power k, and this is not allowed. So, but the plan is as follows. We will first make a coloring of the graph, but I mean just assign a color to all the nodes. We don't care if an edge connects nodes of the same color. So we choose k color and randomly assign colors to the same node. And then we check whether there is a path in which all the nodes are numbered. So the first node has color 1, the second node color 2, 3, and so forth. So for example, was the let's four. The usual graph, and then we want to know whether it has a path of length 3. So we already know the answer, but just to illustrate the algorithm, then we will generate 3 random colors. So I will use 1, 2, and 3 for the names of the colors. And so when we generate, it might be something like this. And then we check whether we can build a path with the colors 1, 2, 3. So we want to find whether we can find somewhere in the graph this thing here. And
The
this
amount of
can be
colors-
done, yeah,
The amount of colors is K.
yeah. And so the question is, how do we know that we can do this in polynomial time? Check that there exists a path like this. So for this, we rewrite the graphs in 3 sets. So we will make all the nodes with color 1, all the nodes with color 2, and all the nodes with color 3.
And we can just run the first from each.
Yeah.
But if we assign the colors randomly, we can get a graph that contains only, for example, for color 1.
Yeah.
One, and it's a problem.
Yeah. So the plan is to do it many times and prove that if we do it enough, then it will be okay. So imagine that our graph indeed has a path of length to it. So let's pick one path. We assume it exists.
What is the distribution of color?
So uniform. Every node gets uniformly
Uniformly
selected.
distributed colors.
Yeah.
How do you do that? Some question before we begin. Can we do it without random, but just learn some simple deterministic algorithm for assignment?
So we can de-randomize, but whether it's simple.
So, but we can do it.
Yeah, we can make it deterministic. I will quickly tell you how it goes.
Okay.
Okay,
Yeah, this is clear.
so now what is probability that we will indeed find? So you get how I build this graph. It's very good, yeah. And so now probability of find the path over the colors. And so I claim that this is 1 minus 1 over k factorial. So we use dy. So we do it once. Yeah, it's more than 1 over k factorial.
Probability of what? Probability of
Probability that we are lucky and that we find a path.
the probability of some step.
Yeah. So we do it once.
Okay.
We assign once random colors,
Yeah.
and then what's the probability that we do have a path?
Do we assume that the graph contains?
Yeah. So we at least one path.
So if the graph contains the path. Okay, so. And we are only looking for paths like directly, like the first node it must be 1, the second node must be 2.
Yeah. So it works even for directed graphs.
So we have this path, and we multiply the probabilities that each of the vertices will get the expected colors.
Yeah.
One divided by.
I'm wrong. Yeah. You're right. So yeah, k to the power.
Yeah.
Yeah. My mistake.
So the probability that the first node gets color 1 is 1 over k.
Yeah.
No, because it should have passing.
Yeah.
One over k colors. The second node
Also 1 over
is
k.
also.
Yeah.
And the length of path is k, so
Yeah.
it's going to be
And so now we know how many times we need to do it before we get 1/2 probability or luck, or 1/t probability to be lucky. And so probability that we fail,
We need to take log k to the power of 3.
Yeah.
K was t.
probability p failures is equal to 1 minus probability that we are lucky in a fixed time. Lucky first time. You write it again. So this 1 minus is equal to 1 minus probability lucky first time to the power. If we have t iterations, t colorings, t random colorings, we get this thing.
We forgot to put the
Yeah.
And then in lucky first time.
Yeah, because the probability we're lucky the second time. I mean, we find path first time. So lucky means find path the first time. And so this is probability we fail the first time times probability we fail the second time times probability we fail and so on. Okay, so what is algorithm? What will be algorithm? We will set t equal to k to the power k, and then we try k to the power k colorings. And so, what is the probability? We have k to the power k failures. It's probability that we fail the first time times probability the second time failure, third time, and so on. And so when we have t attempts, we multiply all these probabilities, and in each attempt, the failure probability is the same.
What are we doing?
Yeah.
Can you please repeat?
Yeah.
From there, like the probability of finding a path given the random coloring,
I want to prove that this is e to the power exponent minus 1. Probability that that we have t failures is smaller than exponent minus 1. So
the probability of not finding a path, given that it exists in the graph after trying t times
and
assigning random colorings.
Yeah.
And so we set like t to the k to the power of 4.
Yeah.
Shall we try?
And now
find one of the probabilities of the 0.5.
Yeah. And so here we use exponent minus 1, so that's even a little bit is smaller than 1,000. Okay. And now we use formula that says 1 plus r is smaller than exponent of r. And so r can be positive or negative. It's some famous formula. Should try to remember this. It's everywhere, especially for cryptography. Yeah, you also have probabilistic algorithms. No, it's easy to prove. So first, exponent Taylor expansion starts with 1 plus r. So you can see that it's for sure when r is positive, it works. And when r is negative, you can compute the derivatives of both sides. So the derivative will be 1 here, and here it will be exponent r. And r the negative. Okay, then you need to think about derivatives. It's easy also. So we will apply this. So okay, we know that probability to fail. There's a probability to find path is bigger than 1 over k to the power k. So we have probability to fail 1 time. It's 1 over k to the power k. which is, oh, so let's use east, which is smaller than exponent and -1/3. And now we take to the power t both sides. So here we take to the power t. So this is equal to exponent -1. This is precisely what we want. So here probability of find path is 1/t here.
Why do we write first on the bottom? We shouldn't, like, we should write 1 minus probability of find path, right? Like I mean in this bracket stuff on the left, find path, and then we write
Yeah.
first time. What does
1 minus find path at the first attempt. So here we speak about t attempts.
we as what
For
is-
the first
what
coloring.
what is an iteration? We assign
One
a,
iteration.
we assign a coloring, and
Yeah.
then we check all possible.
Yeah, that's
So
one.
like first on the
Yeah, so it is probability that we think.
yeah, I got you. So okay, we exclude the условные вероятности.
Yeah.
Conditional probabilities.
Yeah.
So we say that our events are independent.
Yeah, exactly.
Assigning colorings are independent events.
Yeah.
And then so the probability is always 1/k to the power k. And when we t times, and what's to the left is this, to the right is exponent k to the power. And
By the way, I printed the exercises.
okay.
So there are several about coloring.
Okay. Yeah.
So there is exercise with triangle packing, but just if so
However, this example with 1 minus 1 divided by t is not our case because
so here probability is at least 1/t. And so I'm trying to make a lower bound that we all fail. Yeah, sorry for the different places on the board. It's not. So we want to bound this by, let me write it nicely then. In one chain.
So you mean if we do k in the power of k steps, we will achieve what we
Yeah.
need.
And this is smaller than exponent -1/8 times it's exponent -1. This we already understand. It's exponent -1, and this is smaller than 1. And if you want 1/4, then you just do it 2t times. Okay. And so what is the total runtime of our algorithm? It's t times 40n. So it's equal to k to the power k 40n.
So this is acceptable k.
So it's enough for this definition. Yeah,
a computable function.
yeah. So now you roll the coloring
My
technique.
problem is that at the beginning of the course, I didn't understand the definition of computable function completely. So it's given in the book, sixth book.
Ah,
but,
yeah.
I still don't understand.
It's just that Turing machine exists that
Ah.
computes and
Okay.
halts, always halts,
Okay.
and then give the correct output. Like halting problem is not computable.
Given only the input elements.
Yeah.
Started with only input state, always holds with the proper.
Yeah. But then you think about the RAM machine, but it's related to runtime with within a polynomial.
Do we have some non-computable functions?
Yeah, the halting problem. Yeah.
Yeah, I mean,
Or the Busy Beaver function. It's like given a k, the runtime of the slowest program of length at most k on the Turing machine. Yeah, there are people who compute this function as hobby, and it goes very, very fast. Yeah, I was also like overworked. It's okay, I will try to compute it, and it's actually nice to do because there is this Collatz conjecture, and it's like very easy. So to build a tiny Turing machine that checks the Collatz. So this you get the number. If it's even, you divide by 2, and if it's odd, you multiply by 3 and add 1. And so the question is, if you start with any number, will you get down to 1 positive number? Will you go down to 1? Because 1, it gets in a cycle. It goes 1, 2, 1, 2, 1, 2. And so it's extremely difficult problem. So it's open question whether even the set of numbers that go down to 1 is decidable. So nobody knows. And Erde said that no point to work on it. Mathematics is not ready for this question. And so, yeah, he's a very famous mathematician. He died in the 80s, late 80s.
Why in poly n we can decide
For the
it's-
end, it's the time to check that first search.
Yeah. I mean, but it will still be a probability.
A probabilistic algorithm.
Probabilistic.
Oh yeah, there was a question. I almost forget. So how can we make it deterministic? And so what are we using to compute the probabilities here? We only need k-wise independence. So when we write down this probability, we don't, so the plan is to use hash functions. So k-wise independent hash functions. And why can we do it? So that's the only probability we need for a given coloring. So we don't need that all the colors are independent. We just need that any set of k points have independent colors. So if we look to any set of k points, we need them to be independent to get this, because we only multiply. So do you know the difference between independence and pairwise independence, for example? Okay, so if I take 2 random bits, I have 2 random coins, and I consider 3 bits. So coin 1, coin 2, and the XOR of the 2 coins. So then these 3 variables, they are not independent. What I don't need to worry about what I'm explaining now. It's just background information because somebody asked, how do you make it deterministic? So, okay, if you have, but it's very important concept. So these three bits, they are not independent because you cannot make 1, 1, 0. No. 1, 1, 1, you cannot make because the third is the XOR of the other 2.
The third is.
Yeah, so it's definitely not independent. But if we take any 2 bits, they are
Pairwise independent.
yeah, they are independent. So if we take, of course, the 2 original coins, they are independent. But the first coin and the XOR is also independent.
Because the XOR is actually just adding second coin.
Yeah, so yeah, it means you take 1 coin and you look at the inverse of the other coin. If it's 1 and the original, but yeah, they're basically equal. Yeah. Or yeah, I should just say take a copy of the second. Oh no, then they're not all pair. Okay, yeah. So we need to XOR.
If the random variables are pairwise independent, it doesn't mean that they are altogether.
Yeah. And so what's our plan is that with hash functions, that's tactically you use them when you only need pairwise independence. So if you make probabilistic algorithm and you just multiply 2 probabilities and that's it. And for the rest, you use union bound or you add expectations. We did it in approximation in the streaming lecture. We spoke about this. We applied this technique, like transfer to independent hash functions, because we just, in many cases, we only needed variances. That means we were just multiplying two probabilities, and we only needed pairwise independence, nothing more. And so here we can do the same thing. But now we need k-wise independence. And so we will take a set of k-wise independent hash functions. And then try, and instead of taking the probability, we brute force over all choices of the hash function. And then there's a question, how many hash functions do we have? Do we need for this? And this is kind of good news because it is order 2 to the power order k, and then there is some, I forgot about the dependence on n. Poly n should be saved here. So that's the number of hash functions we have. And this is very good news because here we have fewer hash functions than attempts, because t is k to the power k. So if we try all the hash functions, we can, and they're just all the polynomials of degree k. We use as hash function. So here we will look, we will map all the nodes n. We will apply a polynomial of degree k. So we iterate over all polynomials so we pick it's just easy. Take a prime that's a bit larger than n, and then compute modulo n the polynomial. But okay, I will not explain all this. Just saying that it's kind of easy to iterate over all the hash functions. It's just generating all the polynomials modulo some prime number a bit larger than k. Okay, but now we are distracted. But since we explained this, and it's the second time we use it, we can we can speak about these hash functions. With probabilistic algorithm, they're very popular for the randomization. Okay, so now let's so we did this thing. Now dynamic programming, an easy one. Yeah. So our problem is now so we get the universe. So, but maybe you should stand. It will help to get.
No, my eyes is just.
Yeah. So the input is a set U, and then a list of subsets. S1, S2. Till Sn. And they're all subsets of U. And so the question, okay, let's say. So do you understand 2 to the power U? It's all subsets of U.
Mostly.
Yeah. So here is a collection C. U, and then C is equal to this. And the question, can we have a selection of some subsets that covers all of U? So this is strange. Very easy question.
Connection of subsets.
Okay, no, that's
Given size collection.
yeah. Sorry, I will do something better. So let's say that let's not assume they're subsets of U, and then but it's called set cover. It's strange.
Maybe minimum number of sets.
Yeah, you're right. So let us have some other number. Yeah.
Also, if they are not subsets, we can make them subsets.
Yeah, you're right. So those are exist. C prime of C such that So can we select L of these subsets so that all of U is covered by the union? And U,
What is C then?
and so C is the set of subsets, the collection of
Is
sets.
2 to the power
Yeah,
U?
No.
No, or
yeah, I
just some-
removed
just
that.
some-
Yeah,
some
subset.
collection.
yeah, okay, I
It's a
realized.
subset of two. You know.
Yeah, we can add it or not because we're just interested in U being a subset of the union or S and supply of S. Okay, it's a kind of mathematical notation, but it's clear, right? So can we pick L subsets that cover U? So the problem is called subset cover. Sorry, set cover.
Yeah.
Set cover.
Of course, if the union of C doesn't cover U, if the union of all the subsets doesn't cover U, we can.
Yeah. And so if L is a parameter, then it's clearly FPT because oh no, it's not clearly FPT, but our parameter will be the size of U. So here the parameter is size of U. So that means can we have an algorithm that runs in time F size of U times for the n
What is 10?
and the number of sets. So, and this is by dynamic programming. So now let's see if you have an idea.
Просто типа, если S1 покрывает один раз, дальше S1 разделяем с S2, если покрывает.
Не такое, что такое.
Ну, типа, да.
So the asymptotics doesn't depend on this, the number of subsets, not exactly subsets, the size of C.
Yeah, so we can pick out, so C, yeah. So
I
the
think
size of
we-
C can be polynomial dependence.
Mhm.
But we can only be, we can be generous with U.
Oh, okay.
So this suggests that we will have something that runs in time 2 to the power size of U. And so we will do something for all the subsets of U. So we would need to make a table. And then one argument X. So X will be a subset of U. So then usually the table has two coordinates. So what might, okay, I already seen, but what might be the
Если сердце, короче, 0,1 берем, а n это просто сколько нужно проводить.
Да, не еще. Сейчас, еще раз надо. Ну, так если 0,1, то у нас просто строчка получится.
Нет.
Ну, 0,1. Или ты имеешь в виду
Если
типа 2 на n. Ну, вот у нас n по одной координате, n это число этих чего-то.
Ну, n это просто, короче, сколько мы уже их прошли. Не знаю, условно. Уже переключали. И переход, короче. Во-первых, мы первым ставим просто, типа, блин.
Я считаю, что это был размер таблицы.
Я размера, ну как,
Ну, да, какие измерения?
ну можно там абстрактно сказать, что двухмерное.
Нет, я понял, ну
двухмерное
сколько на сколько. Ну, так в итоге, типа, сколько.
Ну, размер U плюс 1.
Это типа тензор размера модуль U, типа у него модуль U
Но это
ног.
огромный хрен.
Нет, подожди, у него модуль U это осей, или
Давай.
модуль U у него это длина?
Ну смотри, условно, у тебя в чатике, как это сказать еще? Я не занимался этим.
Я тебе отдаст со второго курса.
It's something like a Knapsack problem.
Yeah,
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 it's-
yeah,
it's-
indeed,
it's-
yeah. But it's very important. I mean, it's quite often you need to use dynamic programming. At least I need it quite often.
We're not programmers.
I mean, I'm programmer, but I don't use it.
No. Okay, it will come if you a higher level, if you're supervising, you need to tell. Yeah.
I mean, it's just some variant of the Knapsack problem.
Yeah, yeah, yeah. It's also a table.
Смотри, короче, переход. Play режим. Это, короче, вот G, это, короче, индекс интереса. G, это ничего не батон, либо, короче, TP, I это множество. И считаем на G, короче. То есть это мы типа взяли. Или мы не взяли. Да. Вот. Это взяли или не взяли. Почему так не бывает? Это переход. Это теперь макс. И это 1-0. Это не хранить. Да, это переход. Согласен?
Ну, то есть это просто типа один на модуль U будет переменный. Так что, ну, один, в смысле, одна строка, модуль что все. И в каждом.
Сейчас, я это себе представляю, как вот у нас есть S1, S2 и так дальше. И вот это вот. Я просто не помню, что это было.
Что ты просто поделал, какая разница.
Ну да, ну короче. И тут, короче, вот тут. Тут, короче, мы не взяли, тут не взяли.
Ну, да, так вот я
Только
говорю,
это множество.
вот здесь сколько.
Только здесь размерность, да, внутрь. Размерность.
Ну, то есть, короче, это, не, короче,
Вообще,
короче, трехмерный тензор.
Нет, это не трехмерный.
А сколько мерный?
Это U мерный в одну сторону.
Нет, это называется не мерный, это называется, что у него
нет.
размерность здесь, короче, U, здесь у него размерность, я так понимаю, N.
Ну да, да.
А здесь вот тут у него сколько там вертикально? Ну, у тебя
Я понял.
вертикально туда и сюда. Тут и туда.
You don't need tensor.
I don't understand the concept of this table.
I mean,
no.
Okay, so
Yeah.
yeah. So what means T? So we take a subset of U and we wonder whether we can what is minimal number of sets we need among the first and prime sets to cover set X.
да, и здесь еще плюс. Yeah.
So let me write it.
Probably understood something.
So in the table, minimum number of sets among
To cover
X, S and prime to cover X.
What is
Yeah.
X?
X is this argument.
Yeah, it's
So
a
and
subset
prime
of
is
this.
here. Yeah.
It's a subset of minimum.
And so now we
Yeah.
so we will do it column by column. So we start with n prime equal to 0. So that's easy to tell what is X 0 here. So if we have no sets, then we can only cover empty set. So it's equal to and then we need 0 sets if X is empty. And let us say plus infinity. Yeah, otherwise. Okay, and now given a column, we want to understand how can we get the next column.
What does F prime stand for? What is N prime?
And prime here. So we can only use the first n prime set.
Out of C, right?
Yeah, out of Ln. So we order the sets.
Also, so,
Now we want to know what is Tx n prime plus 1.
It's minimum, yeah, minimum of t x without x minus s and
right.
yeah,
Okay, let's do it like this.
yeah. And
N prime.
yeah, minus one, yeah, and just tx
Plus 1.
yeah, plus one, and t just x and n minus one.
Yeah.
And prime minus, yeah.
What is the second coordinate one?
So n prime tells you that you can only use the first n prime sets.
Yeah, so much we already.
Yeah.
Okay.
And then to know, so what is the task? Cover X using the first n prime sets with minimum number of sets. So it will be,
What
this
are
will
the
be a
dimensions?
number.
Am I right that the dimensions of the table are one
Yeah.
or one by n?
2 to the power u times n will be the table, the size of the table. Yeah. So X is a subset of u.
Yeah.
Yeah.
How do we take minimum?
So we take the best way, so the fewest sets we want. So the table will have a number. So a number which is at most n prime if we use all the sets. And at least one, unless X is empty, then yeah.
Okay, so we take the min.
And so our task is cover X. And so there are two cases. Either we take set n prime, and then we are in this case. So then we need other sets to cover X minus Sn prime. Or we don't take X n prime. And then there's this case. We need to cover X with all previous sets. And so this is the minimum number of sets we need to cover X, not using Sn prime.
What is in the table? Like what is written in the table? Like
Yeah, what is the best number of sets we use? So here is what is written. So I wrote it in words here.
Yeah.
Minimal number of sets among S1 till Sn prime to cover X.
Okay, it's a number.
Yeah, it's number.
Each cell has a number.
Yeah.
Cells are indexed in like well, the columns are indexed by the integers from 1 to n prime.
Yeah.
The rows are indexed by
Sets.
by sets.
Subsets of U.
By sets. Okay, so we can just renumber them with integers from 1 to u to the power of this. Okay. Now what do we write in the cell? Like zero plus infinity, and then the transition function from the
And then in the end, of course, we look to U and N. And it will be our answer.
So for each subset of U, we have a column.
A row for each subset of U, a row.
Okay.
Useful lecture.
Very useful.
At least I think it's useful. So this is dynamic programming. We will use it again for the last step if we get there today, maybe next week. Well, probably next week. Next one is branching. And so there is a feedback vertex set problem. It's like in all the books about parameterized complexity. So I will honor all the other teachers, and I never needed this problem. But okay, it's kind of nice. So the input is now a graph again. And the question is, how many vertices do we need to remove to get a tree? So it's called the feedback vertex set problem. Like feedback refers to cycle. If a cycle happens, like if there are microphones or something, if there is a cycle, you can have beeping. If there's a reachability graph, that's kind of directed problem with this undirected training. So input is a graph and number k. Question: can you remove to get? Oh, let's do a little other exercise. So you remember branching. So the problem, it's in the exercise list. So number 4 or no.
Triangle pattern.
No, that's with coloring. There was another thing with being triangle free. Can you remove k points to get triangle free graph? Here, the third exercise. So show that the problem is FPT, just to remember from last week. How would you do it? So can you remove k nodes? And now you end up with triangle free graph. So it's another problem. Here you want a tree, but let's first think about triangle free graph. How will you do it? You will remove k nodes. So how can you prove it's an FPT?
We did something with
Yeah.
remove not triangles, but
Yeah, indeed, you're right. So you need to do the same thing. So to get, so we can get an algorithm that runs in time 3 to the k poly n. It's called branching technique.
Yeah, we branch like that. We pick a node, we either remove it or not, or we remove all the savers.
Yeah, so we search for triangle. If there is no triangle, then we know the answer, triangle, yes. And if there is a triangle, then we try to remove each of the 3 nodes. And so we decrease k by 1, remove one of these nodes, and then repeat. And so, and then the recursion tree each time splits into 3. And since k decreases in each recursive level, the depth is k. And so we get this runtime.
We need to remove exactly k nodes, so that's
At most k
At
nodes,
most.
but in the worst case, each time we remove k.
no.
Remove we want.
If you want.
no, we can. We can
I
use
mean, if you can do in less than k nodes, you can. Your question was.
Yeah.
Okay. And so now here is let's go back to our problem. So we will make a branching algorithm like this. But okay, I will just tell you what's the answer because there is no chance you can guess the lemma. I mean, okay, I should be careful. So I will tell the lemma, you can tell the algorithm. So lemma is, so let's sort the nodes by decreasing degree. D1, D2, and the degree is T1 bigger than T2 and so on. And then the claim is that among the first 3K nodes, there is always a node inside. So every feedback vertex set contains at least one node among the first 3K nodes. This is the lemma. Every feedback vertex set.
The vertex set is like
A set of K nodes that you need
that
to remove.
have a cycle for now.
No,
the
it's
vertex
the
set.
set of K nodes that you need to remove in order to obtain a tree. It's called the feedback vertex. Okay, let us do this again. So this graph has feedback vertex set of size 1.
which is.
Yeah, okay.
Yeah.
Alright.
Yeah, we just no, the top doesn't work.
I mean, top left.
Yeah.
Okay, every feedback vertex.
So I don't say trees now, it should be forest, so cycle 3. Because I mean that the graph might be disconnected afterwards.
Mm, mm.
Every feedback vertex set is with
Contains nodes from, so at least one node from E1 to 2 till to 3.
How do you sort those by,
So by the
decreasing
decreasing degree, so among the 3K nodes with maximal degree, there will be at least one in every feedback vertex set. Wait, it's not true. If all degrees of the graph is at least 3. If if graph connected, I'm not sure. Okay, anyway, if graph has if each node in the graph has degree at least 3. And then every.
But what if we have degrees?
2 nodes. We will use kernel. We will use reduction rules. So okay. So to state the reduction rules, let's use multigraphs. It means that multigraphs. It's called. Two nodes can have parallel edges. Otherwise it's very hard to state the edges can be stacked. So we say these two edges are connected 3 times, 4 times, and so on. And we allow self loop.
This is the first time
Yeah.
I see the problem when self loops are out and it's allowed to stack the edges.
Very useful lecture.
No, it's actually quite a technique.
Yeah, but
Remember, I
otherwise,
even used it to solve.
yes, but otherwise to state the reduction rules, it's hell. And I guess to program also hell. Okay, so what will be the reduction rule to get rid of nodes of degree 0, 1, 2? So remember our problem here. So we don't want to change the answer and just get rid of nodes.
So we can add some additional nodes that just duplicate the existing. We can add some additional edges that just duplicate the existing edges.
Yeah. If you want to go to normal graph,
More edges, so we increase the
the number of nodes.
power of each node.
Yeah, but now I tell you, you're allowed to have the double edges between two nodes.
yeah.
Or
Yeah,
triple, yeah.
Or we can just add self loops for each of these.
Yeah, but we need to do, yeah, to get rid of the grade 3 node and self loops everywhere.
Yeah.
Yeah. Okay, I didn't anticipate this. Okay, good point. It was not the answer from the book.
But if we are allowed to have self loops and we can have two similar edges, does this lemma work in
Okay,
this
yeah.
case?
Yeah, you're right. So here we cannot have self loops. The multiple edges, I don't know. We will need to check the proof. It's allowed multiple edges.
Okay.
So, yeah, but the self loops, no. So we need to,
So if we have if the node has a power 0, we don't care about this.
yeah, we just throw away the node.
Yeah.
So reduction 1. Delete isolated nodes. Reduction 2.
Only the power of the node is 2. We take any 2 or 1. We take any of the node of the edges that are connected to these nodes and just duplicate them as much.
Okay, and let's call it 0 because the degree is 0. Let's write it separately. When the degree is 1, oh, no. We can merge this. Delete isolated nodes and nodes of degree 1.
Yeah.
They cannot be in a cycle. So irrelevant. And
So
then
the
the
reduction
second
is
rule.
just pretty.
Yeah, it's easier. And then the second rule, no, no.
The rule number 2, we just take all the nodes that have degree 2 and
Yeah. Remove it. We need to get rid of these nodes. But if we
sorry
remove
for
it,
interrupting.
no,
Just
no.
listen to.
no, yeah, tell your idea.
Yeah, my idea was just to add any of the edges that these nodes have and just have multiple edges. For instance, we have.
Yeah, I see what you're trying to do. Yeah. Let's add an edge
Yeah,
here,
yeah.
and then we have 3. Yeah. Okay, we
But-
will need to check about multiple edges, but let us say in the book, I don't remember, I cannot tell right away if it works with multiple edges or not. It means I'm a bad teacher. I should go to the proof in 1 second. I have trouble to prepare. So the plan is to remove the node and put an edge here.
Okay, probably works.
Yeah. Yeah. Indeed, it doesn't change anything. But that's why we need multiple edges. Okay, we cannot, sorry, your trick doesn't work? No, now I understand. So what here, let's do this here, but then if you have double edge, it is actually a cycle.
Hmm.
And then we change the answer. That's why we cannot do it.
Okay.
Yeah. It's like what
probably
is
don't
definition
even,
of cycle? Yeah, it's a bit tricky. And here we see what's happening. Like if there is already an edge, we delete the nodes,
And
we
then
create the second edge.
Why do we need to create a second node? If we create a second
No,
edge,
if we just delete this node, we're deleting a cycle and we might change the answer.
okay.
So that's why we need double edges.
So yeah, we want to leave the cycle
Yeah.
when
Yeah.
I'm not sure
Yeah. Delete node of degree 2. And insert item neighbors. And here we only need to do it if there is at most one edge. If there are already two edges, we don't need to create a third edge. But okay, it doesn't matter for anything. And that's it. And so after we do this, then we get the graph of degree, where all nodes have degree 3.
It contains a node from the first three of degrees.
3K.
3K.
Yeah.
Oh.
Okay, now let's check about self loops. So what can happen? Oh, if we have a node like this, whatever, and here are more things in the graph, then we have a node of degree 2. And so it has 2 times the same neighbor. So when we delete this node, we need to add a self loop here. So we need to allow self loops. And now let's hope the proof of the lemma works with self loops. Okay, I think it works.
So
But
now
if it works, we can just add self loops in the first
No,
place.
but then you change the answer because a self loop is also a cycle. Okay, good. Yeah, that's good.
this is not for what the self loops are needed.
Yeah, yeah. but that's how it happens. So imagine that there is a triangle, our graph is a triangle. So what will happen by the rules? We will delete the node and add the cycle here. And then we will do the same thing here. We delete this node, but we need to add the cycle here. Okay, and in this case,
So this lemma works only in certain scenarios of self loops.
yeah. So we need to keep self loop and parallel edges.
But why not? The lemma works, but if we use the
Yeah.
loop in incorrect way, so the lemma, so the graph changes and the answer changes.
Yeah, if you just add self loops, it changes the answer.
Yeah.
So we receive the graph
Yeah.
that is not equivalent to the initial graph.
Yeah, because I need to be careful what is cycle, and so self loop is a cycle, and parallel edges to parallel edges also.
What is the degree of this node?
It's 2.
That's 2. Okay.
So in this
So
case,
if it was 1, we
yeah,
we would just delete it.
yeah,
Like immediately.
yeah. So, but if everything contracts to a single node, so we need to search through. Like if we have such nodes, then we delete it and remove k, but decrease k by 1.
Okay, now we want to do some branching.
Yeah. Yeah.
So we take, so I think at the first step, we just iterate through
Yeah.
each of these 3K nodes and do a recursive call.
Yeah. So we add them to the vertex core. So it means each node, we remove it from the graph and decrease k by 1 and then recurse. And we do it for all these nodes. So what will be the runtime? Is it an FPT?
3K factorial. Yeah.
Not factorial. So we will have a branching so that there will be a tree. And in every node, how many branches?
3K.
No, sorry, you're right. 3K factorial. No, you're not right.
Something like, but not exactly.
Not, yeah. So in the first node, we have 3K branches. And then in the next node,
K minus 1 for each of the 3K nodes.
So in each node, there are 3K branches, because in each,
Ah.
so we remove a node, but then we get a new set of 3K
But
branches.
we have another, the K change, no? The
You're
The
right.
K
The K
reduces,
decreases. Yeah, sorry.
Oh.
Yeah, you're right. 3K factorial is the depth. Right, well. 3K factorial.
no, the depth is just 3K.
Yeah, but the size is 3K factorial because number of children multiplies in each level
Yeah.
by first times 3K, then times 3K minus 1. Yeah, a good point. Yeah, I was wrong. 3K factorial, yeah. Okay. You're good with branching algorithms. So we've done this one.
Gentlemen, let's take a break.
Yeah, but it's time for the break. So then we will do exercises. And next week, I will do these two things. The lower bounds.